Most welcome to 1263 of the series, still recording here in the local church of Bremaregården. Very lovely and inspiring environment indeed. I would today continue, and sorry, it was rather an abrupt termination on 262. Something stopped the camera preemptively. I will continue where I left off. To vindicate the existence of a preferred cosmic time, it does not suffice to show, as I earlier argued, that the thesis of the inclusive reality of time and of the thoroughly historical character of the universe require it. Such an argument would be merely speculative and circular. In the end, what are decisive are the facts of the matter about the universe, its constitution and its history. Is the universe, or is it not, so evolved and arranged that it allows for a preferred cosmic tune? The answer is that the concept of a preferred cosmic time can be translated into the idea of a preferred state of rest of the universe, but only at a cosmic rather than a local scale. The claim that a preferred state of rest exists at local scales would contradict special relativity, for which is an unabundant empirical evidence. The existence of a preferred state of rest gains operational significance and a chance for empirical validation from features of the universe that support preferred or fundamental observers. Observers for whom the universe appears to be expanding and changing equally in all directions and from all directions. Their position is, in this sense, neutral. That there is more than one way of selecting such observers, that the observers selected by these alternative criteria are the same despite the plurality of criteria for selecting them, are powerful signs of the reality of the phenomena that these criteria select. One criterion is the range of frames of reference from which the galaxies recede at the same speed. The second criterion is the range of frames of reference to which the cosmic microwave radiation background of the universe presents itself at the same temperature. A factual condition for the existence of such preferred observers is the relative homogeneity and isotropy of the universe. We cannot infer this condition from theoretical or a priori considerations. Our inability to do so supports the point that the most important feature of the universe is that it is what it is rather than something else. Its features may nevertheless have historical explanations. The applicability of these two overlapping set of criteria for choosing preferred observers of a preferred state of rest in the universe is no mere speculative conjecture. On the Earth, these criteria apply to a close approximation so long as we control for the consequences of the movement of our planet in space. Reconsider in the light of these remarks the objections to the existence of a preferred global time that claim the authority of general relativity. The concomitant effect of these two sets of objections is to shift the burden of proof in favor of the non-global time of the prevalent understanding of general relativity, and against the thesis of a preferred cosmic time. The first set of objections rejects such a time because it is incompatible with the notion of the space-time continuum and its spatialization of time. I later argue that this notion embodies as supra-empirical ontology. The ontology does not deserve to benefit from the authority granted by the classical and post-classical tests of general relativity. On the contrary, we have many reasons to strip from the hard core of general relativity this metaphysical accretion. Of these reasons, the most important are those that concern the inclusive reality of time and the historical character of the universe, and the requirements of a way of thinking and of a research agenda that can do justice to them. A second group of objections denies that the features of the universe that we see as making possible a preferred state of rest and preferred observers have any such significance. It dismisses them as accidental features of the history of the universe without larger consequence. These conditions would, according to this way of thinking, be without theoretical significance. They are not explained by laws and symmetries of nature, nor do they suggest, so far as the present state of scientific knowledge can discern, such symmetries and laws. At best, according to the ideas expressed in the idea of a multiverse, the set of these initial conditions expresses one of the indefinitely large possible variations of nature, even that our mathematical representations fail to select the universe that we actually observe. This objection, however, is self-discrediting. It reveals the dangerous alliance between the practice of the Newtonian paradigm and the spirit of metaphysical rationalism. The view of mathematics as the oracle of nature and the prophet of science joins the same coalition. grant me that the most important fact about the universe is that it is what it is, rather than something else, that the distinction between stipulated in initial conditions and timeless laws, which defines the Newtonian paradigm, lacks legitimate cosmological application, and that we cannot infer the truths of nature from metaphysical preconceptions or mathematical abstractions. At least we cannot infer them except insofar as mathematics helps make explicit the implications of empirically validated discoveries about the workings of nature. On these assumptions, we have no good reason to discount, as bereft of significance for cosmology, characteristics that the one real universe in time actually has. Natural science must seek to explain these characteristics. So much the worse for our present theories if they fail to do so. We then need to come up with better ones. Up to this point, I have discussed the meaning of the idea of preferred cosmic time, explored its importance for the development of the thesis of the inclusive reality of time, and for a historical approach to the universe, and considered objections to its existence. I conclude this introduction of the notion of preferred global time by addressing another way in which preferred cosmic time may be introduced into the canon of our cosmological conceptions. Once again, a crucial point is the apparent irreconcilability of such time with general relativity. The reinterpretation of general relativity in the light of other ideas may reconcile the preponderant part of general relativity, and especially its legacy of empirically validated discoveries with the notion of preferred cosmic time. One such set of ideas is shape dynamics, the character and implications of which Smolin discusses in his part of this book. For the moment, it suffices to say that whereas in general relativity, size is universal and time is relative, in shape dynamics, time is universal and space is relative. The propositions of general relativity can be converted without loss of empirical success into this different language. The path by which shape dynamics reaches an idea of preferred cosmic time is a gauge-fixing condition achieved through constant mean curvature slicing. In addition to reconciling general relativity with preferred cosmic time, shape dynamics has the advantage from the perspective of the agenda defended here of eliminating singularities. As a result, it can be useful to a cosmology that is determined to lift the impediment that an infinite initial state imposes on its historical approach to the universe. Nothing, however, in the following argument turns on the merits and prospects of shape dynamics as a scientific theory in its own right. The allusion to it here serves the purpose of suggesting that the relation of general relativity to the idea of preferred cosmic time is more complicated and ambiguous than it may first appear to be, and cannot be adequately described as a simple, insuperable contradiction. Later in this section, I explore another response to the objections raised by the ruling accounts of general relativity to preferred cosmic time, the separation of the empirically supported core of general relativity from what I argue to be a metaphysical gloss on its discoveries. The major part of this gloss is the idea of a space-time continuum and the spatialization of time that this idea has served. The translation of general relativity into the language of a theory such as shape dynamics, weakening or undermining the obstacle to the acceptance of a preferred cosmic time and the divorce of general relativity from the supra-empirical ontology of the space-time continuum represent alternative routes to the reconciliation of general relativity with preferred time. The second route is more radically revisionist than the first. These two paths may not diverge, but one requires more by way of reconstruction in the agenda of contemporary physics and cosmology, and may go further than the other. The historical character of the universe was discovered and confirmed after both special and general relativity had been proposed and had begun to be vindicated by empirical findings. Quantum mechanics was already in the early stages of its development. In different ways, both these theories, as they came to be understood and worked out, lent support to the diminishment, if not to the denial, of time. The most acute contradiction was with general relativity. For general relativity, under its predominant interpretations, was incompatible with acceptance of the idea of a preferred cosmic time as distinguished from the idea of an array of alternative space-time coordinates, choice among which remains arbitrary from the perspective of the theory. Without making use of the concept of preferred time, we cannot give full and radical meaning to the historical character of the universe or to the reality of time. Before saying more about the significance of this real or apparent contradiction with general relativity, it is useful to remember an important feature shared by special and general relativity. Quantum mechanics and all the most powerful movements of 20th century physics, when they rejected Newton's vision of space and time as an unmoved backdrop to physical events, they reaffirmed the conception of an immutable framework of natural laws. The discovery that the universe has a history, that it is not unchanging and eternal, thus took place in an intellectual setting hostile to the full recognition of time. In fact, in the move from classical mechanics to general relativity and quantum mechanics, physics had become more rather than less resistant to the acceptance of the reality of time. The discovery that the universe has a history had to be cut down to size. It had to be reconciled with ideas limiting the reality of time. One way in which these ideas qualify that reality was by rejecting the concept of preferred cosmic time. Although Newton's laws are in principle time reversible, that time reversibility might be annulled by any of frictions abounding in nature, the subsequent commonplace grounding of the direction or arrow of time in entropy might be seen as another example of the effort to rescue the direction and the reality of time by establishing them on the basis of asymmetries in the workings of nature. absolute time and absolute space remained in classical mechanics the stage on which natural events take place rather than an integral feature of the events themselves. As a relational view, such as Leibniz's would require, only in this diminished sense does Newton's physics make room for a notion of preferred cosmic time. It empties this notion, however, of content as a result of the time reversibility of the laws of classical mechanics, qualified solely by the unexplained facts that may render the operations of nature irreversible in the circumstances of the actual universe. Moreover, the explanatory approach, what we call the Newtonian paradigm, that it shares with subsequent physics, cannot deliver any conception of a history of the regularities and of the structure of nature. Newton's physics assumes a universe without history. With general relativity, under its standard interpretations, the situation changes. It is vital to ask whether the argument about the inclusive reality of time, including the existence of preferred cosmic time, that we present here contradicts general relativity. To the extent that it contradicts general relativity, we must further consider whether what it contradicts is the core of empirically confirmed theory or only the association of the empirical idea with a metaphysical vision, from which the empirical core may be divorced. From the outset, the cosmological consequences of general relativity were subject to dispute. Its inventor was himself uncertain. The crucial point is so simple that it can easily be forgotten. General relativity was a theory about the structure of the universe, not about its history. It was formulated within a tradition of science for which physics and cosmology, viewed as a part or an extension of physics, are structural, not historical sciences. To the extent that this tradition makes any room for history at all, and it is doubtful that it does, it subordinates history to structure. The subsequent discovery that the universe has a history therefore presented a problem for the elucidation of which such structural theories had not been designed. It is unsurprising that the implications of these theories for an understanding of the history of the universe were so controversial. The most influential early class of solutions to the field equations of general relativity, the Friedman-Robertson, Walker-Lemaitre solutions, suggested that the universe must have begun in a singularity in which the gravitational field, and hence the values of density and temperature, must have been infinite. Penrose and Hawking proved the past incompleteness of any solution to the field equations of general relativity that is compatible with the smallest of conditions describing our universe, of which the two most important are that the energy density of matter be positive and that there be a three-dimensional space-like structure on which the universe is expanding everywhere. This proof was widely understood to support the inference of an infinite initial singularity from the field equations. Part of the significance of the notion of an initial infinite singularity was to suggest a theoretical basis for the idea of an absolute beginning of the universe. A beginning, as it were, out of nothing, and thus as well for the emergent or derivative character of time. When these interpretations of general relativity were combined with the relativity of local simultaneities established by special relativity, the result was to imply that the concept of cosmic time had no legitimate place in physics and cosmology. However, this suggestion remained inconclusive until a third element was added to the other two: the relativity of simultaneity and the initial infinite singularity. This third piece of the time-limiting picture was the representation of time as inseparable from space in the language of space-time, depicted as a four-dimensional semi-Riemannian manifold. Right from the start, it was understood by many that the appeal to an initial infinite singularity, rather than describing the inference of an actual state of affairs, amounted to an acknowledgement that general relativity failed to apply or broke down when brought to bear on the extreme events of the very early universe. Among those who share the view that such a singularity could describe no physical state of affairs were Einstein and Lemaitre, despite his association with the FRWA solutions. Lemaitre clearly indicated as far back as 1927 his preference for what he himself described as a cyclic account of the history of the universe. To this idea of the infinite, there corresponded and could correspond no picture of the workings of nature. The infinite tamed by 19th century mathematics has no presence in nature. Yet the conception of mathematics as a shortcut to insight into how nature works, criticized in chapter 6, cast a semblance of legitimacy on the appeal to the infinite, representing what was in effect a mathematical conceit, as if it were a physical conjecture. A major consequence of this appeal to the infinite was to establish an absolute bar to causal inquiry into what happened before or beyond the moment when the values of phenomena pass from the finite to the infinite. However, it is not for this reason alone that the outcome is unsatisfactory. Under this view, the laws of nature hold, regardless of time, until a certain instant close to the formation of the early supercondensed universe. Then, at some unknown moment, they cease to hold. What then hold in their stead is not only unknown, but is also, insofar as it crosses the threshold of the infinite, unknowable. An empirical scientist could be forgiven for regarding such a combination of conjectures as a ramshackle compromise in the explanation of the universe and of its history. At best, an approximation to some yet unformulated and more comprehensive idea. What deserves emphasis is that the more general view would have to be more general with regard to periods or moments in the history of the universe, notwithstanding the resistance to consider time as separate from space. The FRRWL view of the cosmological implications of general relativity was never the only one. On one side, there were also Gödel's solutions to the field equations, which resulted in a universe in which there are closed and cyclic time-like world lines. On their other side came suggestions that general relativity might be interpreted in a way allowing for a preferred state of rest in the universe, and thus for a preferred cosmic time. I think it's a good moment here to round off. It's becoming more and more interesting. I realize now this is grand. It is questioning the unquestionable, because a question you could not even know about, how to define it and how to ask the question. This is what Roberto, Unger and Smolin managed, and I'm so happy to be able to share this and understand it to some part. It opens up a tremendous thinking, tremendous, infinite thinking. It is like opening up a plug in a tube, and all of a sudden, all beauties, all fantastic things can come out that have been previously been trapped for an unknown reason, in an unknown way. And we had to make do with the little trickle of things that came out of the tube, thinking that was everything. Like the song, "Is that all there is?" Thank you very much for your patience. It was quite extraordinary. Do enjoy your afternoon or night. Bye-bye. Inspired environment without a doubt. Hardly gets any nicer.